All right, now we're going to look at the equivalent heating reaction, but for peritectic systems. All right, so the first thing I want us to look at is composition B. So same phase diagram that I've been showing you, but we're switching over and we're looking at this composition B. So I've kind of already told you that this is going to be the peritectic reaction. So what I want you to do is use all the tools that we've talked about and see if you can verify that composition B undergoes a peritectic reaction. And then as well, as you're doing that, see if you can also identify what phases are present at room temperature for this composition B. So pause the video, see if you can come up with the answers to this, and then we'll go through and I'll show you how I got this. All right, so we're back. So let me go ahead and show you this reaction. All right, so the first thing that I want us to look at is the region that we're in. So here I've highlighted composition B, and the region I'm in within this compatibility triangle. So if we look at the phases involved in this compatibility triangle, we see fosterite, safrine, and then also spinel. So it lies within that compatibility triangle. But the invariant point for those three phases is actually here. And it's labeled as a peritectic, but we know that it's a peritectic because it's outside of its own compatibility triangle, right? Remember when we talked about that. So this is outside of its own compatibility triangle, and therefore that puts it as a peritectic reaction. So we know we have a peritectic reaction, and so the fact that this invariant point being outside of that tells us this. All right, so we've just verified that this is a peritectic. So secondly, we want to look at what phases are present at room temperature up to the peritectic temperature. And so to do that, we can again turn to the compatibility triangle. So here I'm actually going to show you all of the compatibility triangles. So again, this is a fairly complicated system, so there's lots of compatibility triangles. But showing you B, we see that we're in this, and this is the compatibility triangle that I showed you on the previous slide. We see that the composition of B is in this compatibility triangle of fosterite, spinel, and corderite. And so we know we're in this region, and so that tells us what phases we have. So basically whatever region we're in here, again, this is the isothermal section below all the critical temperatures. So the fact that we're in this compatibility triangle tells us that at room temperature, when there are no more liquids, these are the three solid phases that we're going to have. And so if I do those amounts, then these are the three phases that I'm going to have. And if I use B as my fulcrum, I can determine the amounts. And so I have 34% spinel, 13 corderite, and 53% fosterite. All right, so now on to the rest of the heating. So we know what we started with at room temperature for this peritectic reaction. And so now we know the first sort of critical thing that's going to happen to this composition B is going to be when it heats up and reaches the peritectic, because below the peritectic, it's still 100% solid. So at the peritectic temperature, we know that we have liquid form. But because this is a peritectic reaction, we also have a solid produced, right? We basically have two solids go to a liquid plus a different solid. That's our sort of peritectic reaction in ternary. So we create liquid, but that also means that we have to create another solid. And so in this case, we're going to talk about what I just showed up here with these lines in a second, but we're going to see that spinel is the other solid that we produce along with the liquid. And so this is our kind of reaction. So this is our very general reaction, right? We have solid 1, solid 2 are consumed to create solid 3 and liquid. So in this case, that means that we consume fosterite and corderite, and we make spinel and liquid above the peritectic reaction. So we're going to talk about how specifically we get these two on the reactant side and these two on the product side, because this isn't super obvious. And the way we do that is by looking at levers for this system. All right, so let me show you this system again. So it's a little confusing up here, but the peritectic temperature, the peritectic composition is up here. And then we know our composition of the solids, so spinel, fosterite, corderite over here. So we have 4 reference points. So this is effectively going to be the starting point, the liquid composition, and then all the other 3 compositional points are for the solids. And so when we create liquid, the composition of the liquid is outside of the compatibility triangle. And that's why we have to compensate by the consumption of 2 of these solids to create the third. And the way we do that is by finding sort of equilibrium between 2 sets, a solid and a liquid and 2 solids. And the way we can do this is by finding sets of these connecting, I can call them tie lines, I guess, that intersect. So for example, if I draw a line between fosterite and corderite, they're going to reach a point here in the middle. And then if I do the same thing for liquid and spinel, and I draw a line between those 2 phases, I see that these 2 lines intersect at a point in the middle somewhere. And so that's the important part here, is that they intersect. And so what that tells us is that fosterite and corderite are being consumed and liquid and spinel are being produced. That's what essentially the links of these lines are going to tell us. So they have to intersect at a point. So just think about another case where if you tried to say that liquid and fosterite were going to be produced and corderite and spinel were going to be consumed, right? I could draw a line between corderite and spinel and liquid and fosterite, but they wouldn't meet in the middle and intersect, and therefore we wouldn't have equilibrium with this reaction that we're drawing. So it's important that they intersect, that these 2 lines intersect at a common point. And so with that, like I said, the links from this central point are also important. So the length from fosterite to the middle is X, liquid to the middle is Z, corderite Y, and then spinel to the middle is W. So to get the fractions of what is being consumed and what is being produced, we're going to use those fractions. So fosterite and corderite are being consumed, and so the fractions consumed are based on those lines. So y over x plus y for fosterite, x over x plus y for corderite. And so this tells us that more corderite is being consumed compared to fosterite, so 72 to 28. And then on the other end, the ratios produced are by the ZW line. And so spinel is Z over Z plus W, so 5% produced, but liquid is 95% produced. So corderite is being consumed the most, liquid is being produced the most, is what this is telling us. All right, so now above the peritectic temperature, we know that corderite is going to be the first solid consumed by those tie lines that we just looked at. And so we know that above the peritectic, then, that's going to be the first solid to be eliminated, and we're going to be left with the liquid, and then spinel and phosphorite. And so we can draw our triangle for those phases, and we can use B as our fulcrum and get the amounts. Oops. And so that's what we have here. So 43% phosphorite, 35% spinel, and 22% liquid at the peritectic composition. All right, so as we go away from the peritectic composition, we've consumed cordarite, and we continue to produce liquid. And so we're going to trace that boundary curve yet again, right? And so that's the boundary curve between spinel and cordarite. Sorry, spinel and phosphorite. And so that is the what we're forming. So we're going to trace that boundary curve between phosphorite and spinel. And so we do that, and again, along the way, we can get to any point and determine the amounts of phases that we have using the continually changing amount of liquid composition. And we're going to do this until, again, you'll notice that we trace this boundary curve until we reach that tie line for the two-phase region. So point B is right here, and the tie line between spinel and B extends to this point. And so we're going to continually consume phosphorite and spinel until we get to this point when all the phosphorite is gone, and then we're going to come back and trace to B. And so at that point, we turn up towards that tie line going to composition B. So ignore this. This is from a couple slides ago. All right. So that, again, we've traced all the way back from room temperature all the way up to this composition B. So at 8,000, above 8,000, we would just have liquid. So this kind of, again, explains what we've had at each step. But again, one of the reasons I wanted to highlight what was happening during heating is that there's a couple tricks we can talk about for phases being consumed and produced, and therefore that helps you understand which phases exist at certain points in the phase diagram.